Hi everyone, and welcome to Chapter 3 lecture for Chem 100, which is all about compounds, which is what happens when we take elements and we combine them and chemically bond them together. So there's two types of chemical bonds that we'll learn about, ionic and covalent. So before we get into this lecture, it's a good idea for you to get out your handy-dandy periodic table because you're going to be referencing it a lot in this lecture. I'll get mine out too. Guess I should have had mine out to begin with. Use this time to get yours as well. Okay, ta-da! All right, so compounds form when atoms of two or more elements chemically combine. So elements, if we look at the periodic table, you'll see there's about 118 different elements. This one's a little bit dated, so it only goes up to 109. But there's about, I think, 118 now. There are, however, millions of different compounds. If you think of the elements on the periodic table as sort of the alphabet with which we can form different compounds, it's kind of like the English language. We have 26 letters, but how many, hundreds of thousands of words can we form with those different letters? Lots. And we do that by combining them in different lengths and in different orders. So although there's a relatively few number of elements, there's a really vast number of compounds. So most of chemistry, a lot of chemistry, and especially biochemistry, which is what we're gearing towards in this course, is about compounds, not elements. So compounds don't just form willy-nilly, just like you can't really string random letters together and call that a word. You can't put a bunch of consonants together, like B, D, F, G, F is not a word. You can't pronounce that. There are certain rules that govern the combining of letters to make words, and also, just like with language, there are certain rules that govern the combining of elements to form compounds. And when it comes to compound formation and elements combining, these rules have everything to do with electrons. So in Chapter 2, when we talked about nuclear radiation, that really mostly had to do with protons and neutrons. We're talking about different isotopes, calculating different isotopes. We're talking about a lot about protons and neutrons. Well, in this chapter, we're going to really see the importance of that third subatomic particle, the electrons. So just a little refresher from Chapter 2. An atom has a nucleus that contains the protons and neutrons, and then the electrons fly around in this cloud space outside of the nucleus that we call the electron cloud. And in this picture, these electrons look like they're orbiting the nucleus in these orbits, which is an overly simplified visual of how electrons are arranged, but it works well for introductory chemistry classes. And these different levels that the electrons reside in are called energy levels or energy shells. And there are certain rules that govern how many electrons live in each of these shells. So the first shell, or the first energy level, all right, we say that the energy level we represent with the letter N. So N equals 1 is the first energy level. And it can contain 2 electrons. So the first shell holds 2 electrons. But after that, each one can hold 8 electrons. That's a little bit, again, of a simplification that if you take a higher level chemistry class, you'll learn is not quite true. But for this class, that is a good basic explanation. Okay, so this outermost shell, whichever one is the outermost shell, in this case, it's the third shell, but in another atom, it might be the fourth or fifth shell. That outer shell has a special name. It's called the valence shell. And the electrons in that shell, or that energy level, are called the valence electrons. And it's these valence electrons, since they're on the outermost part of the atom's surface, they're the ones that are the most important and involved in chemical reactions and chemical bonding. So these are the ones we care the most about. So while in the last chapter we talked about how to count total numbers of protons, neutrons, and electrons, we will still talk about how to count electrons in this chapter, but we care more specifically about these outermost valence electrons. So how do we find valence electrons? Well, we could map out the electrons in an atom. We could do this for potassium. K is potassium. And if you check your periodic table, you'll find K here in group 1, and its atomic number is 19. That means it has 19 protons and 19 electrons. So we could draw those electrons using the rules of filling the shells, where that first shell, I guess I need to pick a pin color here. That first shell has 2 electrons, so I'll draw 2 electrons. All right, but we need to get to 19, so we have 19 minus 2, so now we have 17 left to draw. I can draw 8 of them in the second shell. I have 3 shells out now, okay? 8, so we'll do 1, 2, 3, 4, 5, 6, 7, 8. All right, so that's 10 total electrons. So I have to keep going. Remember, all of these can only fit 8, so I can only put 8 in at a time. So I put in another 8 in this third orbital. And I meant to draw a fourth orbital circle, but I forgot in my animation. So, because now we have 18 electrons. Sorry for my super messy orbital here with my trackpad. All right, so this is the fourth orbit here, and we need one more electron to make 19. So since potassium has 19 protons, if we look at the periodic table, there's a 19 here. That means it has 19 protons. All right, so we know that it also must have 19 electrons. And when we draw them out and we fill these orbitals following the rules of 2 electrons in the first orbit and then 8 in each of the others until we get to 19 electrons, we end up with 1 electron, 1 lone electron sitting in that outer shell or that valence shell. So we would say that potassium has 1 valence. Sorry for my sloppy writing. 1 valence electron. And we can do this for any element, but it can be a bit tedious to draw out these maps or these models for every element when there's actually a really easy way to sort of cheat using your periodic table. So if we look at the periodic table, we just calculated the number of valence electrons that potassium has, and we said potassium has 1 valence electron. Well, guess what group it's in? It's in group 1. Just so happens it's in that group, all group 1 elements have 1 valence electron. You could map them all out and prove it, or you could take my word for it, or you could do both. So all of these guys have 1 valence electron. Group 2, guess what? They all have 2 valence electrons if you map them out. We're going to skip over the transition elements, and we're using the main groups here, so the A groups. So group 3 over here has 3 valence electrons. Group 4, 4 valence electrons. 5, 5 valence electrons, and so on and so forth till group 8, where all of the elements in group 8 have 8 valence electrons, with one exception, and that is helium. So if we drew out helium real quick, all right, helium has 2 protons in its nucleus, and it has 2 electrons in that first shell. 1, 2. But the reason it's over here in the group 8 is because that first shell, remember, is full when it has 2 electrons in it. So what all of the group 8 elements have in common is their valence shell is full. And for most of them, it's full with 8 electrons, but for helium, it's full with 2 electrons. So the group number tells us actually the number of valence electrons. And remember, we're referring to the groups that are labeled 1A, 2A, 3A, 4A, not the group numbering on the bottom here. Okay. Also, the periodic table tells us which is the valence shell. So with potassium a moment ago, the valence shell we saw it was the 4th. Oh, my drawings are gone. Oh well. So we saw that there were 4 rings of electrons. So there were 4 energy levels, and that 4th one was the outermost one. All right, and that's because potassium is in the 4th row or period of the periodic table. So the period number tells us what the valence shell is, what the outermost in other words. So when you get a question that says, how many valence electrons does such and such atom have, does an atom of selenium have, or an atom of barium, you don't have to draw it out to figure it out. You just have to look at the periodic table, and boom, it tells you the answer. So this piece of paper is actually quite a good cheat sheet when you know how to use it and you know what stuff means. So another way we can indicate how many valence electrons an element has is we can use electron dot structures. And this was invented by a scientist with the last name Lewis, and he also invented some line structures we're going to see in a moment. So the Lewis dot structure is just a way to represent valence electrons. So hydrogen is in group 1 on the periodic table. So it has 1 valence electron, so we just draw 1 dot to represent its 1 valence electron. Carbon, skip across, is over here in group 4 on the periodic table. It has 4 valence electrons, so I'm going to draw these 4 valence electrons. And it's standard to sort of draw them in the cardinal directions, north, east, south, west, and draw them singly first. So carbon's dot structure would look like that. Nitrogen's right next to it in group 5. So we're going to draw 5 valence electrons. 1, 2, 3, 4, and 5. So now I've got a pair on top here and 3 single electrons here. Oxygen's the next one over on the periodic table. It's in group 6. So we can draw the dot structure for it by drawing 6 dots around it, one at a time, in a circle. A lot of times you'll see it like this, though. A little more symmetrical. And then we can do fluorine, which is in group 7, which is going to have 7 valence electrons. And we will draw those 7 valence electrons like so. All right, so there's room for 1 more electron. It would max out at 8 valence electrons. So there might be some questions in the homework that just ask you to draw dot structures for different elements. So all you're doing is drawing the chemical symbol, and then you're using dots to indicate how many valence electrons there are. Let's do a practice problem here. So using your periodic table, find each of these. And I'm going to draw out the dot structures. Maybe you pause the video here and do it yourself. I might embed a question in here for you to do on yourself. I'm just going to do the answers and then explain them. Alrighty, so these would be the correct answers. Aluminum on your periodic table is in group 3. Group 3A, I'll say. All right, which means it has 3 valence electrons, so I've drawn 3 single electrons around it. It's not particularly important which sides you draw them on, but they should be 3 single ones. Xenon is in group 8A on the periodic table. It's what we call a noble gas, and it has 8 valence electrons, so I just went ahead and drew 2 on each of the 4 sides. And cesium is a group 1A element. Has 1 valence electron. I put it on the left, but you could really put it on any side and it would be fine. So easy peasy. Use the periodic table as a cheat to tell you how many valence electrons something has. So why do we care about valence electrons? Well, the reason we care is because, again, they're on the outside. They're the ones that actually can interact with neighboring atoms and be involved in chemical reactions. And they also help contribute to the stability of the atom. So ideally, atoms want to have a full valence shell, like the noble gases in this group 8A. All of the elements in group 8 have a full valence shell. So helium has 2 electrons filling its first outer shell, and all these others have 8 valence electrons in their outer shells. So the noble gases were named well before we knew anything about any subatomic particles, much less electrons. But what was well known about these different elements was that they really never reacted with anything else. They rarely formed compounds. They were very inert and not reactive. And so they called them the noble gases, kind of like, because nobility, they don't like commingle with or intermarry with other lesser society. And so these gases are noble because they're like too good to bond with anything else. All right, we go to the other end of the periodic table though, group 1, and these guys only have 1 valence electron, and they really want to have a full valence shell, and so they're pretty unhappy. In fact, everyone else on this periodic table is pretty unhappy, and basically their life goal is to fill their valence shell so that they can be full and happy and complete like the noble gases. So the other items on the periodic table tend to be much more reactive, but particularly the atoms on the far left of the periodic table are very reactive because they're always engaging in reactions to try to get a full valence shell. So there's a couple of ways that atoms can achieve a full valence shell. And since for all atoms besides, so hydrogen and helium are the 2 exceptions. They are full with 2 electrons. But basically everything else is full with 8 electrons. And so the ways that atoms can get 8 electrons is, one way they can do it is they can gain electrons, and then that makes them happy. And they'll do that if they have a lot of electrons already in their valence shell. It's pretty easy to gain 1 or 2. It's harder to lose 6 or 7. If they only have 1 or 2 in their valence shell, then they will lose that electron and they lose that valence shell, and the next shell underneath becomes the valence shell, and now they're full and happy. And then the third way that they can achieve a full octet is they can come together and share electrons. And by sharing electrons, they each can achieve a full octet and be happy. So these different ways of atoms pursuing that octet rule and pursuing that full valence shell is the basis of chemical bonding. And the 2 types of chemical bonds are covalent bonds and ionic bonds. So ionic bonding is what happens when atoms gain or lose electrons. When an atom loses an electron, it ends up becoming positively charged because it's lost a negative charge. And when an atom gains an electron, it becomes negatively charged. And then those positive and negatively charged particles are attracted to each other through opposite attraction. And so we call that an ionic bond, and we call these charged particles ions. That's why we call it an ionic bond. In the case where you have two atoms that decide to share electrons in order to fulfill the octet rule, that is covalent bonding. So the key words I would say here is that ionic bonding involves transfer of electrons, gaining and losing, whereas covalent bonding involves sharing of electrons. So let's talk about ionic bonding first. But first we have to talk about how ions form, what an ion is. So remember we said atoms are just defined as neutral. All atoms are neutral. They have the same number of protons as they do electrons. But if an atom gains or loses electrons, it now becomes charged, and we no longer call it an atom, we call it an ion. So by definition, ions are charged, atoms are neutral. Tums break. All right, so there's two types of ions. There's the negatively charged ones and the positively charged ones. So negatively charged ions form when an atom gains an electron. So chlorine is a classic example. Chlorine is a group 7 element, so it has 7 valence electrons, so it has that one empty spot. It gains an electron, and it gains a -1 charge. So chloride ion has a -1 charge, that negative sign. We call negative ions, we call them anions. So anions is just a word for all negatively charged ions. The other side of the coin is, of course, the positively charged ions. These are going to be elements that have very few valence electrons, and therefore it's easier for them to toss one rather than to gain one. So sodium is a classic example of that. Sodium has 1 valence electron. It's in group 1 of the periodic table. And when it loses that valence electron in the third shell, now it loses that whole third shell. And now its outer shell, its valence shell, is the second shell, and that second shell is full. So it is happy. It has achieved an octet. And by losing a negative charge, it now has 1 more proton than it does electrons, and so now it's positively charged. And we call positively charged ions cations. So my favorite mnemonic to remember, anions are negative and cations are positive, is that cats have paws. So cations are positively charged. All right, so ions are actually really important in and of themselves. They will combine to form compounds that we'll talk about, but they can also exist stably in solution. So sodium, actually pure sodium, atoms of sodium are incredibly reactive, and they're actually a metal, a soft silver metal, and they react extremely violently with water. So pure sodium is actually really dangerous, and you don't come into contact with it in any way, shape, or form in regular life. Most sodium that we come into contact is part of a compound, or it's in its ionic form, sodium ions. So when we talk about like sodium in food, consuming sodium in food, or high sodium levels in your blood, we're talking about sodium ions, because that is actually the most stable state of sodium. That's how it mostly exists, in that ionic form. So same thing with a lot of those group 1 and group 2 elements. They largely exist in their ionic form or as part of a compound. But a lot of these ions are really actually important for the functioning of our body. So calcium is important for forming compounds that build your bones. They're also, the ions though are really important for muscle contraction. Magnesium is also important for muscle contraction and nerve transmission. You also have ions that are important, anions, negatively charged ions that are important in your body. So a lot of the minerals that we eat in our diet, important minerals, are actually they form ions in our body and behave as ions. So let's just do a quick sample problem counting protons and electrons in a couple of ions. So we've got a sodium ion. How many protons are in sodium? Well, remember, we can always figure out protons by using the periodic table. All right, the atomic number, the top number. So sodium is number 11. Remember the joke from last chapter? Do you have 11 protons? Because you're sodium, fine. All right, protons, 11 for sodium. Now, if this was an atom of sodium, it would have 11 electrons, but it's not. It's an ion of sodium, and it has a positive charge, which means there are more protons than there are electrons. And since that positive charge is just one positive charge, that means that there are 10 electrons and 11 protons. We did a little subtraction here. You should be able to figure out the charge by doing subtraction, protons minus electrons. So 11 minus 10 is indeed 1, positive 1. So that's how we figure out that there's 10 electrons. How about this oxygen anion? Protons, always, we get from the periodic table. There are 8 protons in oxygen. And oxygen has a -2 charge. That means it has more electrons than protons, because electrons are negative. And since it's a -2 charge, that means it has 2 extra electrons. All right, again, we can check this with a little subtraction problem. 8 minus 10 is indeed -2. Okay, so you may have some problems that are asking you to calculate protons and electrons in an ion. So since we know that ions form by gaining or losing electrons in order to have a full valence shell, and since we can cheat about numbers of valence electrons using our periodic table, we can also kind of cheat and use the periodic table to figure out what the charge on an ion is going to be for those main group elements. So sodium, our reference one, and everything else in group 1A, they all have 1 valence electron. And so it's a lot easier for them to lose 1 electron than to try to gain 7 electrons to have a full octet. So group 1 elements, they will all lose that 1 electron, and then they'll end up with a positive 1 charge. All right, group 2 elements, they have 2 valence electrons. Easier for them to lose 2 than to gain 6. So they lose 2, and then they end up with a 2+ charge, because they have 2 more protons than they do electrons. Group 3 over here has 3 valence electrons. It'll lose 3 and end up with a positive charge. If you look at your periodic table, you'll see all the elements in groups 1, 2, and 3. They're pretty much all metals. So metals tend to form cations. They tend to lose electrons and form positively charged ions. Then we get over to the non-metal groups on the right side of the periodic table. Nitrogen is a reference one in group 5A. They have 5 valence electrons. So it's easier for them to gain 3 than to try to lose 5. So they're going to start gaining electrons now. Now we're going to have the anion formers on the right side of the periodic table. So nitrogen, or any group 5 element, will gain 3 electrons. Group 6 elements will gain 2 electrons. And group 7 elements will gain 1 electron for a -1 charge, which we just write as negative. We don't need to put the 1 there. The noble gases, however, they're already full. They don't need to gain or lose. So you will never see an ion of a noble gas. They just don't do that. You can make ions, like by subjecting neon to some, I don't know, I'm not that good. I'm not like a lab chemist, but I'm sure you could like run electricity through it or something and make those electrons leave, but you'd have to put energy in. They don't naturally lose electrons or gain electrons because they're already happy. They're full and fulfilled with their full valence shell. This is just another useful visual slide showing you again. Here are all the metals on the left side of the periodic table, and they tend to form positive ions, whereas the non-metals over here in the blue area tend to form negative ions. They tend to gain electrons. And the noble gases in that purple column over there form ions. They have no tendency to form ions because they already have a full valence shell. And then these little cheater numbers up here tell you the different charges of each of these groups. So group 1 typically has a +1 charge because it loses its 1 valence electron. Group 2 typically has a 2+ charge, and so on and so forth. And it might be helpful for you to mark up your own periodic table and sort of write those charges above there to help you when you're doing problems, working homework problems, to get to those answers a little bit quicker. So ions have names, and naming ions is not terribly difficult. It's naming compounds that gets a little harder. But to be able to name compounds, we have to be able to name ions. So for metal ions, or cations, all you do is add the word ion at the end. So sodium atom would be a neutral, but sodium Na+, the ion, would be sodium ion. We go through the group 1 elements here: lithium ion, sodium ion, potassium ion, rubidium ion, so on and so forth. Now for the nonmetals on the right side that form anions, negatively charged ions, we add this suffix "ide" to the end of the element name. So fluorine becomes the fluoride ion in its ionic form. Chlorine, underneath it on the periodic table, would become chloride. Sulfur would become sulfide. So we just add that "ide" suffix. And then the most complicated one to remember is the transition metals. Now the transition metals are all of these guys here in that group B. All right, they're sort of like lower in this little pit of the periodic table, and they're weirdos because they don't necessarily follow any strict rules. Their electrons can do weird things and jump around to different shells, and because of that they can form multiple ions. So copper, for example, can form a +1 or a +2 ion. And so we have to have a way to distinguish or indicate which copper ion we're talking about. And so the example here in this slide is actually with iron and not copper. Iron can form a 2+ ion or a 3+ ion. So we can't just call it the iron ion because there's a couple of different iron ions. So we indicate which one it is by naming the charge using Roman numerals. So Fe2+ is the iron 2 ion, and that 2 just is referring to that charge. And the iron 3 ion is referring to the fact that this ion has a 3+ charge. And we know that the iron is going to have a positive charge because they're still metals. So all of these transition metals, although they can have multiple charges, they'll always form cations, positively charged ions. So let's do a little bit of practice here, naming the following ions. Maybe pause, take a minute to name them yourself, and then I will show you the answers. The first one is calcium. It's a group 2 metal, and it's simply the calcium ion. Oxygen is a nonmetal over on the right side of the periodic table, and so we have to use the suffix naming rule, so it's called the oxide ion. Chromium is a transition metal, if we find it on the periodic table. And so we have to remember with transition metals, indicate the charge using a Roman numeral. So this is called the chromium 3 ion. It's not enough to say chromium ion, you have to use the Roman numeral here. Even though we did not have to use a Roman numeral with either of these guys, only the transition metals. And then lastly, iodine, which is group 7 on the right side of the periodic table. It's a non-metal, so we're going to use that suffix, so it will become the iodide ion. Hopefully you got all of those on your own. And to make it just one more type of ion out there, so these ions that we talked about are for ions from the periodic table. Ions of made from one atom, basically one atom gaining or losing electrons. But sometimes molecules can gain or lose electrons and become charged. And molecules or compounds are made up of more than one atom, more than one element, but they're still ions if they're charged. So we call these polyatomic ions. Poly means many, and it basically means many atoms. They're ions that have many atoms rather than ions that are made from one atom. And this is a table of common polyatomic ions that can be found in your book. Might look a little bit different in the version of the book you guys are working with. You don't need to memorize these. These will be provided for, this table will be provided for you on tests as needed. But what you do need to do is sort of familiarize yourself with the names. And the ones that I have starred are the ones that I would recommend memorizing. And that's because they don't follow this general rule. So one of the ways you can recognize polyatomic ions by their names is they all end in ate or ite. There are no elements that name or that end in ate or ite. So you'll never find one on the periodic table. So ate or ite, if you hear that in a name of an ion, you should think, oh, check the polyatomic ion list and go look at it. But these three are ones that can trick you. Hydroxide ends in "ide," just like all of our non-metal ions will. And so what you'll see hydroxide, and you'll be like looking on your periodic table for where, where's hydroxygen or something, it's not there. Hydroxide's a polyatomic ion, so know that hydroxide is OH minus. Same thing with cyanide. If you're looking for cyanium or something, it's not here. You're never going to find the element here. Cyanide is Cn minus. And then ammonium, which really sounds like an element. A lot of elements end in or onium or ium. So it sounds like an element, but it is not. It is a polyatomic ion. So those three, I definitely encourage you to commit to memory. But otherwise, if you hear ate or ite, check this table. Okay, so now that we understand the different types of ions and how to name them, now we're going to talk about how they can come together to form ionic compounds. So we said that ions can gain or lose electrons, but they don't just spit electrons out into like the air around them and then grab electrons out of the air. If one substance gives away an electron, there needs to be a receiver to receive that electron. So that happens in tandem, the gaining and losing of electrons. So ions are not formed in isolation. So with sodium and fluorine, for example, when they get close together, sodium sees an opportunity, and so does fluorine. Sodium basically gives its electron to fluorine. Now you have a positive ion and a negative ion, and they attract each other through their opposite charges. And that attraction that holds the two of them together, like magnets stuck together, that is an ionic bond. So that attractive force is very strong and holds those two ions together very strongly. So we call that an ionic bond. Now, when ionic bonds form, they form ionic compounds. So you have a sodium ion that has a positive charge and a chloride ion with a negative charge. And those two ions get close together and you end up with an ionic compound, sodium chloride. It contains one sodium and one chloride ion. So these components are charged. The sodium is positively charged, the chlorine is negatively charged, but those charges cancel out. So overall, this ionic compound has no charge, right? There's no charge written up here. Ionic compounds, by definition, have no net charge. So in other words, these ions have to combine in such a way that the charges cancel out. Now, if the two ions have the same but opposite charges, that's easy. Sodium has +1, chlorine has -1, 1 and 1, and done. All right. If you had calcium, let's say you had calcium, which is a group 2 element. We look on a periodic table, so it has a 2+ charge. And let's say oxygen, which has a 2- charge. All right, those are equal but opposite charges. They cancel each other out. So they would form CaO. All right, so those are pretty straightforward. But what happens if the two ions have different number charges? Like one is +1 and the other is -2. Like if you wanted to put sodium and oxygen together, or calcium and chloride together, then we have to do a little math. So in this question I asked, how can we combine calcium, which has a 2+ charge, and fluoride, which has a 1- charge? If we put them together 1 to 1, then the charges wouldn't cancel out. We'd have a positive charge left over. So we need to put them together so that the charges totally cancel out. We have 2 positive charges from the calcium. It has a 2+ charge. All right, and each fluorine has a 1- charge. So if we have 2 fluorines, then that's 2- charges. So our 2+ charge on the calcium, all right, so we have 2+ charge here, and 2 fluorines is basically like saying 2 times -1. All right, and if we add those together, +2 plus -2 equals 0. And that's what we ultimately want, an ionic compound that has no charge. So I like this little puzzle piece analogy too, to show if one ion has a 2+ charge and the other has a 1- charge, you need 2 of those 1- ions in order to sort of cancel out and complete that puzzle. Okay. Sometimes there's a trick that you can do. So if it's you know, the charges are 2 and 1, that's fairly easy to balance. But if the charges are 3 and 2, that's a little bit harder. So there's a shortcut method for this, which is called the crossover approach. So if you have aluminum, which has a 3+ charge, and an oxygen, which has a 2- charge, you need to combine them in such a way that their charges will cancel out. And so essentially what we want is to find like a least common denominator or least common multiple. I can't remember which. All right, so if we multiply 3 by 2, right, so if we have 2, scratch that. If we have 2 aluminum, so we can't do 1 aluminum and an oxygen. We need to get this 3 to be an even number. So if we do 2 times +3, all right, that is 6 plus. And so how can we get 6- charges? If we have 3 oxygens, because 3 times -2 is -6. All right, So the correct combination of aluminum and oxygen, in order to get a neutral or ionic compound that the charges cancel out, we need 2 aluminums and 3 oxygens. All right, so it would look like this: aluminum 2, Al2O3. We use subscripts to indicate how many atoms there are. The crossover technique is that you basically swap those exponents for subscripts on the opposite element. So for aluminum, it has a 3+ charge. Well, in the ionic compound formula, we move that 3 to become the subscript on the oxygen. And we take the 2 from the charge of the oxygen and we make it the subscript on the aluminum. So that's like a shortcut method for some of the more complicated, or just anytime you have 2 different charges, you can do this crossover technique to figure out what the subscripts are. So we're going to do several practice problems now. And these problems ask you to determine the correct formula for the ionic compound that's formed from the following ions. And it gives us the names of the ions. So what we need to do is we need to write out those ions. So a sodium ion. Sodium is Na. And we look at the periodic table. It's in group 1, which means it has a +1 charge when it forms an ion, because it has 1 valence electron that it loses. And we're combining it with sulfide ions. That "ide" ending tells me that we're looking for a nonmetal. So sulfur becomes sulfide. So this is just an ion of sulfur. And sulfur is in group 6. It needs 2 more electrons to have a full octet, so it will have a 2- charge. So when we form this ionic compound, I'll just write out sort of the skeleton here. All right, Na and S, it's going to contain sodium and sulfur. All right, but if it just has 1 sodium and 1 sulfur, those charges are not going to cancel out, because a 1+ charge plus and a 2- charge is going to, this thing would have a negative charge. And we can't have a negative charge. We need it to be neutral. All right, so we can do that crossover technique, where that 2 becomes the subscript of the sodium. And this 1+ charge is a 1. So then you get a 1 subscript here. And we don't write 1 as a subscript, so we just leave it blank. So Na2S. I'm just going to rewrite that and try to make it a little bit neater. Na2S is the correct ionic compound that forms when you combine sodium ions and sulfide ions. This is the only ionic compound that will form from those 2 ions. There's no such thing as Na3S or Na2S3, okay? It's only Na2S. That's the only compound you can make with sodium and sulfur. Magnesium and oxide. Magnesium ions. Magnesium is a group. You'll find it in group 2 on your periodic table. So that means it's going to have a 2+ charge. It has 2 valence electrons that it'll lose and then have a 2+ charge. Oxide, that tells us we're looking at the nonmetals, and it's an ion of oxygen. Oxygen, like sulfur, is in group 6, so it has a 2- charge. All right. Now, when the charges are the same, we don't need to use that crossover technique. They cancel out already. So what we get for the correct ionic formula is just magnesium oxide, MgO. And then the last one here, calcium ions have a 2+ charge, and chloride ions. Chloride is group 7 on the periodic table. It has 7 valence electrons, so it will lose 1, or sorry, it'll gain 1 and end up with a 1- charge, right? Since these 2 are different charges, we can do that crossover method. So if we have a 2 plus calcium, we need 2 chlorines. I could even put a 2 right here to remind you that. You need 2 times 1 to equal -2 to cancel out that +2. So when we write that as a compound formula, though, we move that 2 to be a subscript. Calcium chloride, CaCl2. We're going to do some more practice problems using some of the polyatomic ions. So this is a particularly challenging concept in chemistry, forming ionic compounds. So it's a lot of practice. I'm doing a lot of practice in the lecture. You need to do a lot of practice on your own as well. So first we've got potassium ions. And potassium is group 1. All group 1 elements have a +1 charge. And then we have sulfate. 8 tells me that we need to go look up this ion, that it's a polyatomic ion. Anything ending in 8 or ite, it's going to be a polyatomic ion. I need to go to that table of polyatomic ions and look up sulfate. So I do that. You can flip back in your notes. All right, sulfate. The formula for sulfate is SO4 2-. So it's SO4 and has a 2- charge. All right, so we need to combine these. They do not have equal and opposite charges. Sulfate has a 2- charge. Potassium has a 1+ charge. So we're going to need 2 potassiums to combine with the sulfate in order to make a neutral ionic compound. So that 2 is going to be in the subscript K2SO4. We no longer have any charges. This whole thing is neutral, and those 2 ions have combined to form that neutral substance. The second problem, we have sodium ions. Sodium, like potassium, is in group 1 and has a 1+ charge. And nitrate ions. 8, again, tells me we're working with a polyatomic ion, so I go to that table and I look up nitrate, and I'm pretty sure this is nitrate, NO3 with a 1- charge. And so in this case, it's pretty straightforward. Sodium, 1+, nitrate, 1-. It's 1 to 1, so it's just Na, NO3. And that is the compound. End of story. Easy peasy. I saved the trickiest one for last here. Calcium ions. Calcium is found on the periodic table in group 2. It has a 2+ charge. And hydroxide ions. Ide makes us think we want to go look at the nonmetals on the periodic table, but remember, hydroxide is one of those ones I said you should memorize from the polyatomic ion list. All right, so hydroxide, if you look it up on the table, is OH-. Okay, so if we were making a compound from these 2, for every 1 calcium ion, we need to have 2 hydroxide ions because it has a 1- charge. So we need 2 of these to combine with 1 of these. So we've got calcium, 1 calcium, and we're going to have 2 hydroxides. All right? So here's the thing. If I just put a 2 here, if I say OH2, I'm saying 1 oxygen and 2 hydrogens. That's not 2 hydroxides. This hydroxide, all right, this is all one thing. It's one polyatomic ion. It's one single unit. So if I have 2 of them, I need to indicate clearly that I have 2 OHs. So I need to put parentheses around the OHs so we know that I have 2 OHs, not 1 oxygen and 2 hydrogens. All right. It would not be correct to do something like this. CaO2. O2, H2. All right, that would not be correct because then you're saying you have 2 oxygens and 2 hydrogens, and they could be, you know, willy-nilly around that calcium. All right, so when you have a multiple polyatomic ions, or you need to put a subscript on a polyatomic ion, you have to put it in parentheses. And then you can put the subscript outside the parentheses. All right. So practice, practice, practice these. Lots of practicing so you get it straight. So those are ionic compounds, and that's like a bulk of this chapter, is really talking about how to properly form ionic compounds and name them. Covalent compounds and covalent bonding is the other type of chemical bonding. So remember, ionic bonds involve transfer of electrons, and they involve a cation and an anion. Remember, metals tend to form those positively charged cations, and nonmetals tend to form those negatively charged anions. So ionic bonds usually take place between a metal and a nonmetal, cation and an anion. Covalent bonds, though, usually take place between 2 nonmetals. So if you have a compound that's made up of 2 or more nonmetals, then that's a covalent bond. So you could have questions on the homework or on a test that ask you, is this a ionic compound or a covalent compound? And you could determine that just based on the chemical components. If it's a metal and a nonmetal, then it's ionic. If it's 2 or more nonmetals, then it's covalent. So let's do this quick practice problem. NaBr, sodium, is a metal. Bromine is a nonmetal. So that means that sodium bromide, NaBr, is ionic. I just put an I for that. CCl4, and this 4 should be a subscript. It's just a formatting error. So CCl4, carbon and chlorine are both nonmetals, so that means that this is a covalent compound. And then this one is kind of a trick one. I wouldn't ask you this on a test. But it's the one case where we have all nonmetals. We've got nitrogen, hydrogen, carbon, and nitrogen again, all of which are nonmetals. And so you would think it's covalent, but in fact it's made up of 2 ions. NH4 is ammonium, and Cn is cyanide. It's made up of a cation and an anion. So that one's a little bit tricky. But ammonium's the only positively charged cation, so even with polyatomic ions in there, usually you have a metal for a cation. All right, so covalent bonds involve, of course, sharing of electrons, not taking and receiving of electrons. So covalent bonds do still follow that octet rule. Bonding is all about fulfilling that octet rule and filling your valence shell so that you can be noble and at peace like the noble gases. So here's an example with 2 fluorine atoms, each of which have 7 valence electrons. All right, so they each need 1 more. And by coming together and each contributing 1 electron, all right, they're sharing those 2 electrons, and if they're sharing them, we count it around both of the atoms. So we could say that the fluorine on the left has 1, 2, 3, 4, 5, 6, 7, 8 valence electrons, and the fluorine on the right also has 1, 2, 3, 4, 5, 6, 7, 8. So it fulfills that octet rule. Now, can I watch this video? I just think this is a cute little video showing how zen a couple of fluorine atoms become once they form that covalent bond. There's the happy noble gas neon. It's all zen as his valence shell is full. There's neon being too good to form a bond. So sometimes having a full valence shell is referred to as having a noble gas configuration. It's another way of saying a full valence shell. All right. So when covalent bonds form, remember they're still fulfilling that octet rule. And I like to use the electron dot structures to sort of show you how many covalent bonds an atom will form based on its number of valence electrons. So hydrogen has one valence electron, and it can take one more because it has only one shell that can contain, it fills up with 2 electrons. So it can have one bond. So I like to say, like, it can hold hands with something. It's got one hand sticking out to form a covalent bond, or one bonding arm. Carbon has 4 valence electrons, and so it has the potential for bonding arms in order to complete its octet. And it can do that in multiple ways. It can have 4 single bonds, or it could have 2 single bonds and a double bond. It could have 2 double bonds, or it could have a single bond and a triple bond. So there's a lot of different configurations that carbon can make. You could think of carbon as sort of an elemental gymnast. It's very flexible, lots of potential bonding partners, which will come to be more important in the next chapter, chapter 4. Nitrogen has 5 valence electrons, so it has 3 vacancies, or possible 3 different bonds. Oxygen has 2 vacancies, so it can have 2 bonds, and fluorine has 1 vacancy, so it can have 1 bond. So the number of bonds that these nonmetals can have is determined by how many valence electrons they have and how many electrons they need to share. And so this is a good table to star in your notes and use in your homework, but ultimately to really memorize the different bonding patterns that these different groups can have. So this is going to be true, this carbon bonding pattern is true for all group 4A elements. And this nitrogen bonding pattern is true for all group 5A elements because they all have the same valence electron structure. So covalent bonding, Lewis came up with this handy-dandy dot structure, but now when we're talking about covalent bonding, we want to show the number of these covalent bonds, and we use a line to determine that. So if we have 2 chlorine atoms that each have a single electron sticking out that needs a partner, you bring them close together, and now those electrons form a pair. And if we count all of these electrons around the chlorine atoms, each chlorine atom has 8 electrons around it, and we count this shared pair twice, once for each chlorine. So we call this pair right here that the chlorines are sharing, we call it a bonding pair. All of these other pairs around the chlorines that are not shared are called lone pair electrons. They belong only to that one chlorine. All right, so I like to think of those vacant spots as like these invisible arms that stick out with hands, and they can grab hands with another atom that has a invisible arm and hand sticking out. So these two chlorine atoms kind of reach out and grab hands, and then we can replace those hands with a bond, a line here. And what that line actually represents, it's just another way to show that bonding pair. So what it actually represents is those two electrons that are shared. So a bond line actually represents two electrons, a bonding pair. Now each of these chlorines has a full octet and it's happy, just like those two little fluorine atoms in the video. So we can draw these structures, these covalent compound structures of Lewis bonds. We call them Lewis structures, and they show the bonding patterns that covalent compounds have. So let's look at a slightly larger one, but still a small covalent compound, which is methane, CH4. So the way I break it down is to draw all the atoms, so all of the hydrogens and the one carbon, so there's 4 hydrogens and 1 carbon, and then draw the bonding arms that they each have. So each of those hydrogens has 1 vacancy, so it can have 1 bonding arm, and the carbon has 4 vacancies, so it can have 4 bonding arms. And then you just systematically stick them together. So there happen to be 4 places on the carbon and 4 hydrogens to pop on there. So we pop those hydrogens, each of those hydrogens takes 1 of carbon's hands, and we end up with CH4. We can write that in Lewis structure as a C with 4 lines coming out of it, each of those lines connecting to a hydrogen. Each of those lines representing 2 electrons that are shared between each of those hydrogens and carbons. So if we count, this hydrogen has 2 electrons around it, that it's full, its valence shell is full with those 2, and that's true for all of those hydrogens. And the carbon has 2, 4, 6, 8 valence electrons around it, so it has fulfilled its octet rule with 8 electrons through sharing with those hydrogens. So we're going to do a sample problem. I'm going to show you how to draw some Lewis structures here. So nitrogen, we know nitrogen has 5 valence electrons. All right, and I'm just going to draw the dot structure. All right, so that means it has 3 potential bonding arms and 1 lone pair of electrons just sticking out. All right, then we have 3 hydrogens that also each have 1 arm, so that's perfect. We can distribute each of those 3 hydrogens here around those 3 bonding arms of the nitrogen. And now everyone has a full octet. Each of the hydrogens actually has 2 electrons that it's sharing in that bond, and the nitrogen has 2 lone electrons, or 1 lone pair, and 3 bonding pairs for a total of 8 electrons. That fulfills the octet rule. Here we've got carbon, 2 carbons. So I'll draw 2 carbons, and each has 4 bonding arms. 1, 2, 3, 4. Now carbons, when there's multiple carbons, they're usually bonded to each other. So I'm just going to make them join these 2 hands. So there's a bond right there between 2 carbons. And now we have 4 hydrogens to distribute. But we have 6 bonding arms hanging out into space. So I'm going to distribute these symmetrically. So each carbon's going to get 2 hydrogens. So now we have all the 4 hydrogens accounted for, but we still have these arms waving out that are holding on to nothing. And they need to hold on to something. But what they can do is hold on to each other. So we can form a second bond between the 2 carbons. And I don't have an eraser function, so I'm just erasing these. Okay, basically I made those 2 hold hands again. So what we have here is carbon, 2 carbons that are double bonded together, and then single bonded each to 2 hydrogens. And everyone here now has a full octet. The the carbons have 8 electrons around them and the hydrogens have 2. Yay, that's a Lewis structure. And then lastly, we have nitrogen, 2 nitrogens. So nitrogen, of course, has a lone pair and 3 bonding arms. And this one also has a lone pair and 3 bonding arms. All right, so we'll connect these 2 bonding arms first of all. There's nothing else here to bind to these bonding arms, so they must connect to each other. So these 2 arms connect, and these 2 arms connect. And so essentially what we have is 1, 2, 3 bonds between those 2 nitrogens. So we can clean that up and draw it more cleanly as a triple bond there between the 2 nitrogens. And then we don't want to forget our little lone pair that is also there, because this only represents 6 shared electrons, and we know that these nitrogens need 8 to fulfill their octet, so they do need to have that lone pair showing. So that's Lewis structure building for you. Again, practice, practice, practice. Watch extra videos if you need to, but I think that's enough sample problems for now. So when we have covalent bonds, we say that covalent bonds are electrons being shared between 2 atoms. But if you have, like, siblings or friends that you share things with, it's very rare that you share things equally, right? So usually there's a hog in the relationship. Someone is hogging the thing that's shared, like with kids, you always have a toy hog, all right? So same thing with electrons. 2 atoms might share equally, but a lot of times they don't share equally. One of them hogs the electrons in that shared pair. So you can think of that bond between 2 atoms as almost more like a tug of war on those electrons. And sometimes they're an evenly matched set of, both atoms have the same strength of pull on electrons, and so that tug of war doesn't go anywhere and those electrons are shared equally. But sometimes one has a greater pull and they hog and pull the electrons closer to them. And so that the sort of measurement of the strength that an atom has on pulling electrons is called its electronegativity. So all atoms on the periodic table get assigned an electronegativity value. And this is just showing the main group ones. So group 1A, 2A, skip over the transitions to 3A, 4A, 5A, 6A, 7A. And so when these guys enter bonds together, if their electronegativity values are very different, then that means the stronger one's going to pull on those electrons. And if they're very similar or the same, then they will share equally. So the 4 biggest, the 4 elements that have the highest electronegativity values, or the highest pull strength for electrons, are fluorine, oxygen, nitrogen, and chlorine, in that order. And so you should memorize these 4. And my mnemonic for it is phone call, because that's what it looks like, F-O-N-C-L. Phone call are the 4 electron hogs. So if we look at sorry, that's my alarm for a live session. I'm going to make it. Okay, if we look at a equal sharing situation, we've got 2 hydrogens. All right, hydrogens, but all hydrogens have the same electronegativity. So if you have 2 of the same element, no matter what the element is, bonded together, they will pull equally. Carbon and hydrogen have slightly different electronegativities, but carbon is not that much higher or stronger than hydrogen, so we still say that they share pretty evenly. So when the sharing is even, or the electronegativity is pretty close or the same, we call that a nonpolar bond. All right, so nonpolar bonds share electrons equally. they have roughly equal electronegativities, or the difference between the electronegativities is 0.3 or less, like we see with carbon and hydrogen. Polar covalent bonds involve some hogging, okay? So chlorine and hydrogen, all right, are not sharing equally. There's a 0.9 difference between their electronegativity values. Chlorine is quite a bit stronger than hydrogen. And so what happens is chlorine hogs those electrons. The electrons end up being pulled towards the chlorine atom. Kind of like a custody battle between parents where like one, so like nonpolar situation would be 50-50 shared custody, and a polar situation would be like, 20-80 shared custody. So they're shared, kids are shared, but not quite equally. So this funky looking arrow with like the plus shape at the end shows us the direction that the electrons are being pulled toward. So they always point toward the electron hog, the bigger hog, and that arrow is called a dipole moment. And because chlorine is hogging those negatively charged electrons, it ends up being slightly negatively charged. And so this funky little shape here is actually the Greek letter delta, and it means partial. So the chlorine is partially negatively charged, and the hydrogen is partially positively charged. So it's polar because it has these two oppositely charged poles. So that's why we call it polar. Now what can be kind of counterintuitive is that polar is shared unequally and nonpolar is shared equally. And that's kind of counterintuitive because you tend to want to pair up the two, like so nonpolar, unequal, both of those words, you instinctively kind of want to pair those up, but they don't go together. Polar is unequal sharing. It's hogging that causes these different poles to form. Whereas nonpolar is equal sharing, so there are no poles that form. Okay, so the cool thing about polarity is it also explains ionic bonds. So if we think about it, there's really not covalent bonds and ionic bonds. They are all just differences on a spectrum of polarity. So if you have two atoms that have equal polarity, so let's say, I'm going to even say fluorine. All right, it's an electron hog, but if you have two fluorines together, they share equally. All right, and that's a nonpolar molecule. They're nonpolar covalent bond. If you have two that share unequally, like let's say this is fluorine and this is hydrogen over here. All right, fluorine's a big hog. It's going to hog all those electrons from hydrogen. It'll be slightly negative, and the hydrogen will be slightly positive. Remember, hydrogen, although it's on the left side of the periodic table, is still a non-metal, so it still forms a covalent bond. But if that fluorine gets together with a metal like sodium, all right, then it's such a big hog, such a big electronegativity difference that it actually pulls an electron away from sodium, and it becomes negatively charged, the sodium becomes positively charged, and they end up getting together through ionic bonding. So it's, I think, kind of a neat concept to think of that, oh, it's not really two separate covalent and ionic bonds, though we can talk about them, they're very different. But they both occur for the same reason. They both occur due to electronegativity differences and pull of atoms on electrons. And as that pull gets greater and greater, the bond becomes more and more ionic. And as that pull becomes more even, the bond becomes more covalent. So for each of these, we're just going to practice drawing the dipole moment and labeling those partial charges. So essentially we're trying to identify the electron hog, the biggest electron hog. So remember, the big electron hogs are phone call, FONCL, in that order. So if these guys are paired with any other nonmetal, then you know they're hogging electrons. So here we've got a bond between nitrogen and carbon. Nitrogen is an electron hog, carbon is not. So nitrogen is going to hog those electrons, and that arrow sort of points to where the electrons are moving, and that means the nitrogen will be partially negative, and the carbon will be partially positive. All right. In the second example here, we have nitrogen and oxygen. Well, both of these are electron hogs. All right, but their difference in electronegativity is still big enough for it to be polar. So oxygen, this is in order, remember, so fluorine's the most electronegative, then oxygen, then nitrogen. So of the two, oxygen is stronger, has a higher electronegativity, so it will hog the electrons. So we draw the arrow pointing towards the oxygen, oops, and oxygen will be negatively charged because it's hogging electrons, which are negative, and the nitrogen will be positively charged. And then phosphorus and fluorine. Fluorine is the hog, phosphorus is not, so this is an obvious one. Fluorine will be negative, and phosphorus will be partially positive. So remember those little partial notations. They're not truly ions. They don't have a full charge. They just have a partial charge because electrons spend more time around the fluorine, less time with the phosphorus parent. So the last thing in this chapter is just a little bit about molecule shapes. We're not going to get into it, but when we draw Lewis structures on paper, they're two-dimensional. But in real life, in the real world, molecules are three-dimensional. So that methane molecule that we drew before looks like this in space. So it's 4 hydrogens sticking out. Basically, atoms like their personal space. And so they're going to spread apart. They like to social distance, if you will. So they will spread apart as much as they possibly can so that each of those hydrogens can have the most personal space around that carbon in 3 dimensions. And that affects, so we can talk about bond polarity, but we can also talk about molecule polarity. And in the next chapter, we're going to be starting to talk about bigger and bigger molecules. And so we need to be able to determine whether they are polar or not, because polarity, as we're going to see, really determines some of the types of chemical reactions and physical properties of different elements. So we're still sticking with that rule about those 4 electron hogs. Phone call, FONCL, all right, and so a general rule of thumb that you can use in this class, and this isn't always true, but to simplify it for this class, molecules that contain one of the electron hogs, we're going to say are polar. They usually are. There are exceptions, but we're not going to get into those exceptions in this level of chemistry. So propane, it has all carbons and hydrogens. Those guys share pretty evenly. So this molecule on the whole is nonpolar. I'm just going to write non-P, okay? There's no electron hogs to be had. Ethanol, however, has an oxygen, which is a hog, and it's going to hog electrons from other atoms around it. So this molecule will be polar. And urea also has a couple of hogs. It's got some nitrogens, it's got this oxygen. It's going to be pretty darn polar, all right, because of all of those electron hogs. So in general, when you're identifying whether a molecule, it gives you molecules and says, is it polar or nonpolar? It's polar if you can find an electron hog there. Now again, this is not completely 100% true. If you go on further in chemistry, you'll learn the further details. But for this class, it will always be true. If there's an electron hog, the molecule is polar. All right. Oh, and I have the answers animated in there. And then the last thing I can't leave out, but we're not really going to get into in this course, is the mole. So mole is just a number. It's like a dozen A dozen means 12 of something. A mole means 6.02 times 10 to the 23rd of something. And it was coined by a scientist named Avogadro. And so we call this number Avogadro's number. And this is just a funny picture of Avogadro with a mole animal on his shoulder because he came up with this number called the mole. And it's just how, it's like a super, super big number. I'll let you read those fun facts for yourself. But it's how we convert the mass of an atom into the molar mass, which is something we use in calculations. So one atom is so infinitesimally small, if you wanted to like count atoms, you can't. But if you know how many moles are in a certain mass, you can count atoms if you know the mass. So it's how we convert the mass from the periodic table in atomic mass units. So carbon is 12.01 atomic mass units, one atom, or an average carbon atom. And if you have a mole, 6.022 times 10 to the 23rd carbon atoms, it will weigh 12.01 grams. So a mole is just a number like a dozen. You might want to know what that number is, but we're not going to do calculations with it in this class. And that is the end of Chapter 3. Thanks for watching. See you next time.